Okay, let's talk about infinite limits. Now, I want you to keep in mind here that the definition of a limit is that as x gets closer and closer to some x value a, then your y values f of x get closer and closer to some real number L. So when we say we have an infinite limit, it's not really a limit because you can't get closer to infinity. That doesn't really make any sense. So we're going to write things like what you see right here about a limit equaling infinity. That's really an abuse of notation. It's not really equaling a limit. It's just a way of describing behavior. We're just telling people, look, we know this limit doesn't exist. We know that the function's not approaching some value, but we still want to give you some information about what's going on. And that information might be that the function's getting bigger and bigger as our x is approaching some value, or getting smaller and smaller toward negative infinity. So just keep that in mind. These infinite limits are not true limits. They just describe an asymptotic behavior. So we can define these from the left and the right, just like we did with regular limits. So you can pause and read these definitions if you want. But here we're saying as x gets closer and closer to some value a from the left, that my function values are getting bigger and bigger and bigger, tending toward infinity. And that equal was not a real equal there. Again, this is an abuse of notation. It doesn't really equal infinity. That's just how we write it to express that information to the reader. And similarly, if my function's going down, we might say we're approaching negative infinity, and we can approach from the right instead. Remember, the little plus means you're coming from the right. The little minus means you're coming from the left. And if both of those happen to agree, then we might write the limit as x approaches a of f of x equals infinity, or if we're going down, negative infinity. But just like I said here, that does not mean the limit exists. What that means is your function is growing without bound, either toward positive or negative infinity. It's not a true limit. And that equal sign that we're going to write is kind of a lie. Because later we're going to have a bunch of theorems about if a limit exists, then we can do such and such. And in all of those theorems, the limit has to actually exist and be a finite number. So these infinite limits will not apply in those theorems. Okay, so let's take a look at some of these. We know what this guy's graph looks like. A lot of times these infinite limits are best understood by looking at a graph. Like if you're in Calc 1, you should know what the graph of 1 over x looks like, right? Looks something like that. So here on this one, here's 0, the y-axis. I want to be to the left of 0. That's what the little minus means. We're coming from the left. So I'm over here. I'm looking at these x values. Here's maybe x equals -1 right here. What are my y values doing? They're asymptotically approaching negative infinity. I have a vertical asymptote here. That's what all these infinite limits are. They're vertical asymptotes. So this part of the graph is going toward negative infinity. This part of the graph, now I'm still trying to get to x equals 0. I'm trying to approach this, but I'm coming from the other direction. The little plus means you're coming from the right. What's this chunk of the graph doing? It's going toward positive infinity. Now, neither of those limits really exist. A limit is a number, and infinities are not numbers. I mean, I'm still going to write this because it conveys information. But again, this equal sign is kind of a lie. It's not a true limit. However, for us to even write that equal sign on this one that just says, okay, what's the limit as we approach 0? The limit doesn't exist under any definition of existing. First off, the function's not approaching a number. Secondly, even if we're going to have an infinite limit, we don't even have the same infinite limit. These are different. So this one just completely does not exist. Whereas this guy here, as we approach from the left, our graph is going bigger and bigger toward positive infinity. And as we approach from the right, same thing. Here, we could say that the limit equals infinity. Again, it doesn't really equal anything, but we can still write that down. And we could see that in a table as well. So I have the function 1 over x minus 2 squared here in my calculator. I've set my table up starting at 1.5, and I'm going by 0.1s. And now if I do second table, I can see as I'm coming from below, getting closer and closer to x equals 2, my y values are getting bigger. And as I'm coming from the other direction, getting smaller, closer and closer to 2, the y values are getting bigger. Now, remember, anytime you're using a table to evaluate a limit, it's just guesswork. A table never proves a limit exists. It tells you that there's more work to do. So if I wanted to convince myself a little more, maybe I would get closer to 2 from both sides. So I could maybe say, let's start at 1.9 and go by 0.01. So here I only can see the values below 2. This would be my limit from the left. And I can see my y values as I'm getting closer to x equals 2. My y values are getting pretty big. That's a pretty good hint that my limit is going to infinity. And we could check on the top as well. So maybe if we start, maybe I could tell it start at 2, even though I know the function's not defined at 2. See, we get an error there, but as I'm coming in from above, going down toward 2, I can see my y values. Look at those numbers. They're getting bigger and bigger. So it appears both from the graph and from looking at the table that this function is approaching infinity from both sides. Now, here are some rules you can just memorize. When you have an even power of x minus a in the denominator, your graph's always going to kind of look like this. So 1 over x minus a to the 4th, it's going to look a lot like the 1 over x minus a squared. We're going to shoot up to infinity from both sides. But if that power down there is odd, you're going to get something that looks like 1 over x. And you're going to go to negative infinity on the left and positive infinity on the right. And these are rules you can just use now forever. Like, I've given you this information. This will always be true. Now you can just use it. And these happen because we have vertical asymptotes at those points. That's a good place to stop.